Today we're going to talk about certain functions between groups. So we start with a definition, and we start with two groups, G and H, and a function, phi, that's a Greek letter phi, from G to H. I wrote here a map, but a map is just a fancy way of saying function. Mathematicians like to say map sometimes and reserve the word function for certain types of maps. In any case, a map is really just nothing else for us but a function. So a map from phi from G to H is called a homomorphism, sometimes a group homomorphism, if it preserves the group operation. What that means is, if I take any two elements G1 and G2 in G, and I apply phi to their product, see, I wrote a little g underneath the star here just to emphasize that that's the binary operation in the group G. Of course, even without me writing that g there, it would have to be the case because both G1 and G2 are elements of big G, so where else could I have multiplied them? So, but just to emphasize, G1 and G2 are elements of G, so I'm using the binary operation in G. So I take phi of the product of G1 and G2, and I get the product of phi of G1 and phi of G2. So phi of G1, right, that is already an element of H. And phi of G2, that's also an element of H. So now I'm multiplying them as elements of the group H. So a function from G to H is a homomorphism if it carries a product of two elements in G into product of their images. So phi of G1, G2 is equal to phi of G1 times phi of G2. A homomorphism that is bijective is called an isomorphism. So a bijective homomorphism is an isomorphism. Before we get to examples, there's some very basic properties of homomorphisms, actually of isomorphisms here, that I wanted to emphasize. So let G, H, and K be groups. And here's an exercise for you to do. It's a very easy exercise, but I recommend doing it. If I take an isomorphism from G to H, so in other words, a bijective homomorphism, then because it's a bijection, it has an inverse. We know all bijections have inverse maps. So if I denote this inverse by phi inverse, then that's a map from H to G. We know that this is automatically also a bijection. But I claim this is also an isomorphism. Yeah, if this is an isomorphism, then so is its inverse map. Then its inverse map is also an isomorphism. So what is there to check? So phi inverse, because phi is a bijection, phi inverse is automatically a bijection, so we know we already have satisfied this requirement, bijectivity. So the only thing you need to check is that if phi preserves preserves group operation, then so does phi inverse, right? So you need to check. That phi inverse of H1 star H2 is phi inverse of H1 star phi inverse of H2. This multiplication now happens in H, and this multiplication happens in G. Second, sort of a first example of an isomorphism for us is the identity map from the group G to G. Identity map, remember, just takes an element little g and maps it back to little g. Of course, it's a bijection. You just want to check that it preserves multiplication, preserves the group operation. And finally, if I have a homomorphism from G to H and another one from H to K, isomorphisms, then I claim that their composite is also an isomorphism. So you need to check that it's a homomorphism and a bijection. In fact, this exercise here works also for homomorphisms. So if these are isomorphisms or homomorphisms, then psi compose. So if phi and psi are just homomorphisms, then psi composed with phi is also a homomorphism. If there are both isomorphisms, then psi composed with phi is also an isomorphism. This allows us to, those of you who know about relations, this here means that the existence of an isomorphism between two groups is an equivalence relation. So we can make the following definition. Let G and H be groups. If there exists an isomorphism phi from G to H, then we say that G is isomorphic to H. We denote this by this symbol. This kind of looks like an equality, but the top bar is a wiggle. And by these properties that we just showed here, or you will have shown, we get that, first of all, by the property 2, G is isomorphic to G. If G is isomorphic to H, then H is isomorphic to G. Because if I have an isomorphism from G to H, then the inverse map will give me isomorphism from H to G. And so this, and if G is isomorphic to H, H is isomorphic to K, then G is isomorphic to K. So we have these three properties, which means that isomorphism is an equivalence relation. So isomorphism, or being isomorphic, maybe I should say, being isomorphic. Why do we care? Isomorphisms, groups that are isomorphic are not really fundamentally different from a point of view of group theory. In fact, in a sense, if G is isomorphic to H, and I am only a person who is able to distinguish objects based on group theory, then I cannot distinguish between G and H. So from the point of a group theories, G and H look exactly the same if they're isomorphic. So in other words, this property allows us to say when two groups are really different from the point of view of group theory, and when they are actually kind of the same, really the same from the point of view of group theory. You will see in examples that there might be two objects that look differently because they are actually different from a point of view of mathematics, all of mathematics. But if you just want to look at them through the lens of group theory, they are actually isomorphic, which means through that lens you would not be able to say which of them are different. It's kind of like, imagine that you're an astronomer and you're observing two distant stars, and you're using, say, only certain type of telescope, and through that telescope the stars look exactly the same. They have the same size, the same brightness, and then so you would say that if you're only using the technology of that telescope, these two stars look identical. You cannot distinguish between them. If somebody showed you a picture of one star made through that telescope and of another star, of the other star made through the same telescope, you would say, I cannot tell them apart. I cannot say if this is just a picture of, if this is the picture of the first star or of the second star. But you might, for example, now look a sort of take a wider lens telescope that shows not only that star but also the neighboring stars. And now you would see that the constellation around the first star is different from the constellation on the second star. And now suddenly you can actually distinguish between them. You can say, well, these are definitely different stars. However, to do this, you used something other than the technology of that telescope. So it's kind of like this here. Sort of, you can imagine group theory as being a certain tool, a certain telescope, a certain machine that allows you to look at certain objects and say, okay, through that machine, these two objects look different. They're definitely therefore different objects. Like if you look through that telescope and you saw, oh, the first star is much brighter than the other one, you already know they're different stars. But now, if you look through the machinery of group theory and two objects look the same, then they might be different objects from a point of view of mathematics, all of mathematics. But from the point of view of group theory, you say, I cannot distinguish between them. They're the same. And it is often one of the goals of a theory, an algebraic theory, is to classify objects with respect to various ways of looking at them. So here we're going to look at various groups from the point of view of group theory, and we want to say, oh, these are definitely different, but these, from the point of group theory, look the same. The different ones would be called non-isomorphic, while the ones that look the same from the point of view of group theory would be called isomorphic. I don't want to say they're equal, because they might not be the same object, but they look isomorphic, which means indistinguishable from the point of view of group theory. There are no tools in group theory to distinguish between these two objects. You need tools from other parts of mathematics to distinguish between them. And you will see in a moment examples. So maybe let me just say here this one sentence. Isomorphic groups are indistinguishable from the point of view of group theory. So let us look at examples now of homomorphisms and isomorphisms. So, examples. So the first example is the one we already mentioned. If G is a group, then phi from G to G given by phi of G is equal to G is an isomorphism. The identity isomorphism. Okay, clearly a bijection, and I asked you to check that it actually has the property of being a homomorphism. Another example in this sense as well is, this sort of trivial sense is the trivial homomorphism. So let G and H be groups. Then phi from G to H given by phi of G equal to the identity in H is a homomorphism. It isn't an isomorphism unless the two groups just consist of one element. But given any two groups, if I ask you to find an example of a homomorphism, that one always works. You just send everything to the identity. It's like the constant function. Let's check that this is a homomorphism. This is actually quite easy. So I need to check this, that if G1 and G2 are in G, then I look at phi of G1 star G2. I'm going to now drop the star and just write G1, G2. That means in between them there's the binary operation of the group G. Well, on the one hand, G1 and G2 is just an element of G, so by definition this is EH. And if I look at phi of G1, phi of G2, now this multiplication here happens in the group H, but both of them just give me the identity in H. So it's the identity in H times the identity in H according to the definition, so that's just the identity in H. So look, these two things are the same. This and that is the same. So phi of G1, G2 is equal to phi of G1, phi of G2. So that proves that phi is a homomorphism. It's actually usually easy to show that something is a homomorphism if it is, because it's just checking this one condition. If I multiply before applying the homomorphism, is it the same as if I apply the homomorphisms to the elements separately and multiply after? In this case it is. So this is the trivial homomorphism. The trivial homomorphism. That homomorphism here is the trivial homomorphism. Okay, so we have the identity map when both groups are the same, and then given any two groups you have the trivial homomorphism. Are there any more interesting examples of homomorphisms? You bet there are. So, example 3. So I'm looking at the homomorphism from the integers, the map from integers to integers, and here the operation, the group operation is addition, and here the group operation is also addition. Then I'm going to define it given by phi of A is equal to A plus A. Okay? A different way to write it is just 2A. Either way is fine. Is this a homomorphism? Let's check. Phi of, so if A and B are in Z, then, so you have to compute two things, right? What's phi of A plus B? So the operation here is addition, so that's why I'm doing phi of A plus B. By definition, that's A plus B plus A plus B, right? That's the definition of the homomorphism. And then I need to do phi of A, and what's the operation here? It's also addition, plus phi of B. What is that? Well, phi of A is A plus A, and phi of B is B plus B. This is just addition of integers here, right? So you see both of these are actually the same. So phi of A plus B is equal to phi of A plus phi of B. So phi is a homomorphism. Let's check if it's an isomorphism. Is it injective? Injective, remember, different elements go to different elements. Different integers, when I multiply by 2, different integers, when I multiply them by 2, go to different integers. So surely it's injective. Is it surjective, though? No, it's not surjective, because the only thing I can get here are, in the range, are even integers. So you can never get an odd integer. this way. So is a homomorphism which is injective but not surjective. So it is not an isomorphism. Note that, of course, Z is isomorphic to itself. Z is isomorphic to Z via the identity isomorphism. But this particular isomorphism, which doubles every element, this particular map, which doubles every element, is not an isomorphism. It is, however, a homomorphism. And in fact, you could just use phi of A being equal to A plus A plus A, or phi of A equal to negative A. You can check that all of these are actually homomorphisms. Let's look at another one. 4. Phi from Z to Z mod nz. So let n be an integer. N be an integer greater than 1. Okay? So phi given by phi of A is equal to A plus nz. Now, is this a homomorphism? Let's check. What do I need to check? I need to check, right? So I need to check. So if A and B are in Z, we need to check if phi of A plus B is equal to phi of A plus phi of B. Note, right, this addition is in the integers, and this addition is happening here. So this is the addition of congruence classes. Again, when I just write Z as a group, I mean Z with addition. And when I write Z mod nz as a group, again, I just mean it as a group with addition of congruence classes. All right, so let's check that. So phi of A plus B, by definition of what it is, it's just A plus B plus nz. And what's phi of A plus phi of B? Well, phi of A is A plus nz, and phi of B is B plus nz. Are these two things the same? Yes, by definition of how you add congruence classes. So, this. So, indeed, phi of A plus B is equal to phi of A plus phi of B. So this is a homomorphism. Is it an isomorphism? Is it bijective? To be bijective, you need to be injective and surjective. So is it injective? No, it's not, right? Because, for example, 0 and n are mapped to the same thing. 0 will be mapped to nz, and n will be mapped to n plus nz, which is the same as nz. So not injective. Is it surjective? Can you get every congruence class as the image of some integer? Yeah, sure, right? Imagine if n was, for example, 3. There are 3 congruence classes mod 3. 3z, 1 plus 3z, and 2 plus 3z. 3z is phi of 0. 1 plus 3z is phi of 1. 2 plus 3z is phi of 2. And so on. I mean, if n was different than 3, you'd have more of those. But surely you can get every element like this from that sort of map. So, is a homomorphism which is surjective but not injective. Right, let's look at more examples. So example 5. from Z cross to Z mod 2Z. First of all, what's the binary operation here? Multiplication. These are the units in Z. What's the binary operation here? It's the addition of congruence classes mod 2. So what would this map be given by? Remember, this is just 1 and minus 1, right? There are only two elements here. So given by phi of 1 is 2Z, and phi of minus 1 is 1 plus 2Z. Now, is this a homomorphism? Because I didn't really give you a nice formula, I have to somehow check it by hand, every possible element. But there are not so many of them. So I need to check this. So I want phi of 1 times 1 to be phi of 1 times phi of 1. Sorry, plus phi of 1, right? Remember this. See, I fell into my own trap. This is... The operation here is multiplication, but the operation here is addition of congruence classes. So the times should get transformed into a plus. What else? Phi of minus 1 times 1 is equal to phi of minus 1 plus phi of 1. And finally, phi of minus 1 times minus 1 is phi of minus 1 plus phi of minus 1. I want all three to be true, right? These are all the possible combinations you can get. 1 with 1, minus 1 with 1, and minus 1 with minus 1. Let's check. All right, so phi of 1 times 1, 1 times 1 is 1, so that will be 2Z. Minus 1 times 1, that's minus 1, so that's 1 plus 2Z. And here minus 1 times minus 1 is 1, so that should be 2Z. Now let's check the other side. Phi of 1 is 2Z. Phi of 1 is 2Z. And that checks out. 2Z is equal to 2Z plus 2Z. Let's check this one. Phi of minus 1, that's 1 plus 2Z. And phi of 1 is 2Z. So when I add these two, I do get 1 plus 2Z. So that checks out too. And finally, phi of minus 1 is 1 plus 2Z. And here again, I get 1 plus 2Z. Oh, but if I add them together, I do get 2Z. So this one checks out too. So this is a homomorphism.